we already know about the properties of exponents. We just want to look at them in a context of rational exponents, of fractional powers instead today. So remember that the product property is if we see multiplication, we add the powers together. If we see division in the quotient property, we subtract those powers. If we have a power to a power, then we're going to multiply those two powers together. That comes from our order of operations, which if we saw one thing, we did what was right below it. For the power of a product and the power of a quotient, that just means we take the power and bring it into each of the factors inside the parentheses. And then lastly, the negative powers, it just says to make a power go from negative to positive, put it on the other side of the fraction. What I'm going to do now is just look at a lot of examples on simplifying exponential expressions, things that got fractional powers in them, and we're going to use those properties to help us simplify. Like here we have 7 to the 1/4 times 7 to the 1/2, and we see multiplication, so what we're going to want to do with the powers is add them together. But the thing is, we're not dealing with whole numbers anymore. Now we're dealing with fractions, so we have to remember how to add fractions together, and that is to get common denominators. And we'll have 7 to the 1/4 plus 2/4, and our answer will be 7 to the 3/4. Here we see division, so we're going to want to subtract. But remember, our power in the numerator, when we just have 5, is 1. So that's going to be 5 to the 1 minus 1/3. 1 minus 1/3 is 2/3, and we're done. In this example, I know you see multiplication, so you might want to add those powers together, but we can't because the bases aren't the same. So we go down to the power of a product property, where we take this squared and bring it inside. So 6 to the 1/2 is going to get squared, and 8 to the 1/3 is going to get squared. Now, for each of these, we have the power of a power, so we're going to take these powers and multiply them together. And 1/2 of 2 is just 1. 1/3 times 2 is 2/3. We can go a little further here, and looking at 8 to the 2/3, that's the cubed root of 8 squared. 8 squared, that's just 64, and the cubed root of that is 4. So we can simplify this even more and write it as 24. Once again, here we see division, so we might want to subtract them powers, but they're not the same base, so we can't do that. So let's bring this 2 inside to each of the factors. And we'll have 42 to the 2/3 and 6 to the 2/3. Now, this isn't very well simplified, and the thing about properties is that they work in both directions, and we just use the power of a quotient property to bring that squared inside to the numerator and the denominator. Now I'm going to kind of undo that as well and take that power out again. So we'll have 42 over 6 all to the 2/3 power. And if you look, aren't these two expressions the same? Make sure that you understand that they are the same, that I can also take a power out of a fraction as well as bring it inside. Because now we can simplify this 42 divided by 6, that's just 7. And this will simplify to 7 to the 2/3 power. Let's try one more of this type where we bring that 1/3 inside to each of our factors. We'll have 27 to the 1/3 power times p to the 3rd to the 1/3 power times q to the 12th to the 1/3 power. Now 27 to the 1/3 just means the cubed root of 27. 3 times a third is 1, and 12 times a third is 4. So we can simplify the whole expression. The cubed root of 27, that's 3 p q to the 4th. Remember when it came to square roots, there was a couple of things we said about simplifying square roots. That we couldn't have any perfect square factors inside, and we couldn't have any radicals in the denominator of a fraction. Well, those ideas still transfer to roots with larger indices, right? A bigger index. So instead, not just square roots, but also cubed roots. And it's just now when we have a cubed root, we're not looking for perfect square factors, we're looking for perfect cube factors. So what I'm going to want to do with this radical is to break it up into two roots again. by looking at that x to the fifth. And see, x to the fifth is x to the third times x squared. Remember our product property, which says that if we were multiplying these two together, we would add the powers. So 3 plus 2 is 5. So that's why I can break it up like this. Now, I can literally break up the radical into the cubed root of x cubed times the cubed root of x squared. The cubed root of x cubed, well, those guys just cancel. And now we're at x times the cubed root of x squared. Right? And this is a simplified radical. So let's do it with a big ugly one. First, break up each factor. And we'll have not the cubed root, but the fifth root of 4 times the fifth root of a to the eighth times the fifth root of b to the 14 times the fifth root of c to the fifth. Right. The fifth root of 4, that's not going to simplify at all. So I'm just going to leave that there. But now when we look at a to the eighth, the fifth root of a to the eighth, that's going to be the fifth root of a to the fifth times the fifth root of a to the third. For our b's, that's going to be the fifth root of b to the fifth times the fifth root of b to the fifth times the fifth root of b to the fourth. Because 5 plus 5 plus 4 makes 14. And then lastly, I'm going to keep that fifth root of c to the fifth right there. Simplifying the whole thing now. Our fifth root of 4 doesn't simplify at all. But here, 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 and here, all four of these have the fifth root of a fifth power, so they're all going to cancel. And so we'll have an a b, another b, and a c. And then what we're left with will be just a couple more roots. Fifth root of a to the third, and the fifth root of b to the fourth. So let's combine this all together and simplify it out. Right here we have a, b squared, c. And all together under the fifth root, we'll have a 4, an a, and a b to the fourth. And then it's simplified. Last one, how about a fraction? Right now, we'll have a radical in the denominator of our fraction, which we're not allowed to have. You see, we break this up into the cubed root of x over the cubed root of y to the 8th. And what we're going to need is a denominator that doesn't have a root in it, a cubed root in this case. So what I'm going to multiply by is the cubed root of y down here. When I multiply them two together, we'll end up with the cubed root of y to the 9th, which will simplify. So whatever I do to the denominator, we also have to do to the numerator. So in the numerator, we'll have the cubed root of xy, and in the denominator, we'll have the cubed root of y to the 9th. We could, what we can do now is simplify this denominator, and that's the last step. So we'll have the cubed root of xy in the numerator, and the cubed root of y to the 9th is just y cubed. Let me take a second and illustrate that one more way. When we have the cubed root of y to the 9th, see, we can look at that as a rational exponent, where that would be 9 over 3. And what's 9 over 3? 3. That's how we'll get the denominator of y cubed.